Now, so far I am assuming that most of the time these sensors are actually generating continuous values in continuous time. Since our computers are processing discrete values in discrete time, that means samples, sequences of values, we have to use discretization. Now, the first thing that we are doing usually is discretization of time. That means that we replace this continuous domain there by a discrete time domain, and we need some circuit that provides that conversion from the continuous time domain to the discrete time domain. This conversion is feasible with so-called sample and hold circuits. Sample and hold circuits are very simple circuits. They just consist of a clock transistor and a capacitor, and the capacitor will store these sequence values. So this device is very simple. You see over here this little transistor there that can be closed or opened depending on the value of the clock signal which we apply there. And assuming that we're closing the switch, which is an abstraction of this transistor, assuming that we are closing that switch, we will transfer the corresponding voltage to that capacitor. We will charge the capacitor according to the input voltage there if the switch is closed and not open, like in this little graph over here. As a result, what will happen is the following. Assume that we are starting with a signal which is a function over the continuous domain. As a result, we will get a sequence of values, or we will get a function over a discrete time domain. What actually happens is that at the time when we close the switch, we will charge the capacitor, and we will transfer the voltage onto the capacitor, and it will essentially stay there until we close that switch for the very next time. And then hopefully very quickly we will be charging or discharging the capacitor there to the new value, and the new value will then stay there on the capacitor as long as that switch is open. And when we close the switch again, we will transfer the new voltage again onto the capacitor, and it will stay there on the capacitor essentially unchanged until we close that switch again, and at that time we will transfer the new voltage onto that capacitor. And as a result, we would be getting these sequences of values that correspond to the little dots that I put here into this graph. So the original signal is a mapping from the real domain onto the real domain, whereas the new sequence, I call it h of t, is a mapping from some discrete domain, and typically we use integers for representing the discrete domain, from that discrete domain onto the real domain. Now, the question that I would like to address next is, do we lose any information due to the sampling? That means to taking samples at these instances in time. This means would we be able to reconstruct input signals from the sampled signals? And in order to answer that question, I'd like to first of all to teach you how we can approximate different signals by sine waves, and we will then see that I can answer this question by answering the question for each of the sine waves. So first of all, I have to convince you that indeed it is feasible to approximate arbitrary signals by sums of sine waves. What I will be doing here is a certain limited view into the theory of Fourier approximation. We don't really have the time to go into the mathematical details of Fourier approximation. I can only show you by examples that indeed it seems to work, and in this way I'm trying to convince you that the mathematical details would indeed convince us that my statements will be true. So I'd like to demonstrate that we can approximate arbitrary functions by sine waves, and we are starting with a case that seems to be rather difficult because we try to approximate a square wave. We try to approximate a square wave that has a certain period. We try to approximate a square wave which has a period of 4. And according to the theory of Fourier approximation, we are able to approximate such a square wave with a sum of sine waves that have different periods. So according to the theory, we have to use these coefficients in order to do this approximation, and the approximation becomes better and better if we increase the value of k. So if we use more and more of these sine waves of higher and higher frequencies or shorter and shorter periods, we will be approximating the square wave much more closely. So we start with a single sine wave there, which has the same period as the square wave, but obviously it's not yet approximating really a square wave. So next we consider the case of k equals 3, where we have added another sine wave that has a frequency that's 3 times the frequency of the sine wave that we see over here. And we see that the resulting signal is becoming a little more similar to the square wave. Now we repeat this for more and more sine waves. So in this case, for this graph, we have added a sine wave that has 5 times the frequency of the original sine wave. And we see that this approximation is improving. In this graph, we have used a sine wave that has 7 times the frequency of the original frequency. And again, we see that this is becoming more and more similar to a square wave. And when we add more sine waves of higher frequency, we see that we are approximating the square wave better and better. I'd like to show you a little applet that you can use through the internet in order to really see how we can approximate different waves. So there's this website whose URL is also listed on the slide, and there we can select between different pulses, and there we can also select how many coefficients of approximating sine waves we would like to use. For example, in this case, the goal is to approximate this rectangular pulse using 10 different coefficients, and we can see that for 10 different coefficients we are actually somehow approximating this rectangular pulse, but we can also use more efficients, and there we can see that the approximation becomes superior to the previous one. There is some artifact there at these transitions. The theory would tell us that these artifacts do not completely disappear. So we can also use other pulses like these, for example, where we would see that with less coefficients, the approximation would obviously be less precise. So there we see a larger deviation from the intended signal. So in this way we can demonstrate how we can approximate different functions using sine wave. So that is something which I did not describe in mathematical detail, because there we would need to discuss the entire theory of Fourier approximation, for which we don't have enough time in this course. So we assume that in this way we can indeed approximate arbitrary signals by sums of sine waves. And the next thing that I would like to do is I would like to constrain myself to the consideration of linear transformations on signals. That means that signal processing is assumed to just perform linear transformations. Now, what's a linear transformation on signals? A transformation, that means a certain function applied to one of these signals, is called linear if the transformation applied to the sum of two signals is equal to the transformation applied to each of these signals separately, and the resulting values then added. These linear transformations are what we consider in many of the cases. Most of the analog circuits did provide linear transformations, and also if we have digital processing of the information, we do in many cases use linear transformations. So in the following, we will therefore constrain ourselves to using linear transformations. And this, in fact, allows us to consider sums of sine waves instead of the original signals. And that was the whole target of our exercise. I wanted to demonstrate that in the following, we can just consider sums of sine waves instead of considering the different original signals. Now let's look at two different sums of sine waves. These two signals there, the one shown in this with this interrupted line, and the one shown with this continuous line, they are both representing signals that have different contributions there in terms of sine waves. So we have two contributions there for this function shown with one continuous line. And we have three different contributions there, three different sine waves for that line showing with this with the dashed line, for the function shown with dashed line. So, and now at this time, I'd like to assume that we are sampling these two functions at integer instance in time. That means at these integer times, I'm assuming that we are sampling these two functions. And you can see by looking at these two functions and by looking at these integer times that both functions have exactly the same value at all integer times, which means that we cannot distinguish between these two functions. It means that obviously we are not sampling these functions frequently enough to actually distinguish between these two functions. So if we are sampling at these integer times, then we cannot distinguish between these two functions. Now, next I'd like to demonstrate that this is actually something that I can demonstrate by using an audio example. I'd like to use an audio example there where I am using a signal that has increasing frequencies, and we will see that if we sample this signal frequently enough, we will actually be able to hear all the frequencies. However, next I will reduce the sampling rate. That means I will reduce the number of times that we will sample the signal, and it will then become obvious that some high tones appear as if they were low tones, and this is because the changes that happen in between the sampling instance are not really captured by the way that we are doing the sampling. So first of all, I'd like to demonstrate this increasing tone. That means I'd like to demonstrate the case where we're sampling frequently enough so that we can distinguish between the sine waves of all the different frequencies. So one more time. So next I decrease the sampling frequency to just half of the original, and I'm playing this sweep again. So during the second half of this signal, some very high tones sounded like low tones because we are not sampling frequently enough. And now we are reducing the frequency that we're using for the sampling, and we will hear that even more tones appear as if they were low tones. And just one more time. Okay, so I think that was an audible result of an experiment demonstrating that indeed if we are not sampling frequently enough, we will be considering some signals that contain some high frequency components as signals that only contain low frequency components. And the question actually is, how frequently do we have to sample so that this so-called aliasing effect, this mixing up of high sequences with low sequences, does not happen. And there, sampling theory does actually help us. So according to the theory of sampling, the following can be stated. If we are not sampling frequently enough, then reconstruction is impossible, and the question is, how frequently do we have to sample? And sampling theory provides us with the so-called Nyquist criterion, and according to the Nyquist criterion, aliasing can be avoided if we restrict the frequencies of the incoming signal to less than half of the sampling rate. That means the period of this sampling rate must be less than half of the period of the fastest sine wave that we have in our input signal, or phrased in a different way, the frequency of the sampling signal must exceed twice the highest frequency that we have available there in our input signal. This highest frequency that's available there in our input signal is called the Nyquist frequency, and the frequency that we're using for sampling is called the sampling rate. So that means we have to make sure that input signals of high frequencies do not really exist in our input signal. And we have to use filters to avoid this aliasing. So that means that most of the cases we are using so-called anti-aliasing filters that are placed in front of the sample and hold circuits, and they make sure that this mixing up of signals with two different frequencies does not happen. So such a filter should not have any impact on the voltage of the incoming signal until we are reaching half of the sampling frequency, and thereafter no contribution should actually pass through that filter. That would mean that we would be requiring that very steep decrease of the fraction of the input voltage that is passed there onto the output of the filter. However, such a filter with such a steep decrease does not exist. We can prove that it cannot exist, and that we have to be happy with just providing approximations. So any realizable filter will just be an approximation there, which means that the attenuation of the input signal will already start a little earlier before half of the sampling frequency. And if we are beyond half of the sampling frequency, we will still have small contributions there from the input signal. So if we use such a filter, especially if we use an ideal filter, then we would be changing that signal that is shown with dashed lines into the signal which is shown with these solid lines over there. So therefore we see that exactly this type of aliasing is avoided with this anti-aliasing filter. Now, anti-aliasing is not only important in the cases that I've mentioned so far, it's also important in computer graphics. As an example, I'd like to show these two little pictures over there, where on the left-hand side we have a picture that has been integrated there onto the slide with a very high resolution, and there we can see that this wall looks very natural. However, we can add the same picture with only a restricted number of pixels. And we do this on the right hand side, and there you see if we just reduce the number of pixels but do not apply any filtering, we can have this aliasing, and this aliasing leads to considering or leads to the impression that there is some low frequency optical wave there on the picture, on the right picture there. And that is a result of not using such an anti-aliasing filter. And if you have worked with pictures that on your computer, you might have run across possibilities of using filters there.